In this lesson, we will be doing an introduction to what a differential equation is. We've already looked at them a little bit this year, but we're going to be formally studying it in this unit. And then we'll also introduce what a slope field is. In this lesson, we'll be identifying a slope field and attaching it to a differential equation. And then in the subsequent lesson, we will be actually sketching slope fields, rough sketches by hand. Okay, so what are differential equations? Actually, they are just exactly like their name suggests, differential. We know that that goes along with derivatives, so they're equations that are derivatives. Okay, so they're equations that are derivatives. There's actually courses out there, and if you end up going into some kind of a math or engineering field, you'll have to take a class called differential equations, where you'll actually just be studying how to solve and work with differential equations. Well, why are they so important? Well, remember, derivatives represent rates of change. Well, lots of things out in the world are constantly changing, so that's why differential equations are so important to the field of calculus and science. So when they talk about like how to find a solution to a differential equation or what are the solutions, what they're referring to is, so we know a differential equation is a derivative. When they ask you to solve it, they want you to find the original function. In other words, take the antiderivative. So we will be reviewing our integrating skills in this chapter as well. So there's two different types of solutions, just to put them into categories. When you solve a differential equation, you might get either the general solution or the particular solution. The general solution contains an unknown constant, which is like the plus c. So then your answer represents many functions since there's an unknown constant in there. They're all in a certain family of functions, but it's not referring to one specific function. Whereas the particular solution, you found what that constant is, and so your answer is a unique function or just an exact or a particular answer. So that's where particular comes in. So general solutions has a constant in it, an unknown constant, and a particular solution does not. All right, so then one of the things that you'll be asked to do commonly is determine whether or not a function is a solution to a differential equation. So what we're going to do is we're going to see if we can make this criteria here too. So what this says is that the second derivative minus the original equation are equal to 0. So I need to find the second derivative right away to check to see, because I need it for this. So anyway, so the first derivative, of sine would be cosine. The second derivative would be negative sine. So I want to check to see, is the second derivative minus the original equal to 0. So the second derivative minus the original, because that's y equals sine of x, is equal to negative 2 sine of x, which is not equal to 0. So no, this one is not a solution to that differential equation. Okay, let's try the next one. So the first derivative by chain rule, because I have a negative x up there, would be 4 e to the negative x times negative 1 by chain rule. So negative 4 e to the negative x. So the derivative of that then would be negative 4 e to the negative x times negative 1. So that would turn out to be 4 e to the negative x. So now I want to check y double prime minus y. Does that equal 0? So here's the second derivative minus the original, and that difference is 0. So yes, this function is a particular solution to that differential equation. So let's try with this and see that. Notice that there's a c in there. There's a constant. So the derivative of this would be c e to the x. The derivative of that would be c e to the x. So the second derivative minus the original function is also equal to 0. So yes. What's important to note about this is that would mean that anything in the form of a constant times e to the x would be a solution to this differential equation. So here's just another example. So verify the equation is a solution to the differential equation and then find the particular solution. All right, so we want to show that that equation meets the criteria of 2 times the first derivative plus the original function equals 0. The word verify implies that it should work. So if we know y is equal to c e to the negative x over 2, we need to find the first derivative for this. That's something that's important. All right, so c e to the negative x over 2 times, and then I have chain rule, so times a negative a half. All right, so I need to do 2y prime, so 2 times my first derivative plus my original function. The 2 and the half end up canceling, so I end up with negative c e to the negative x over 2 plus c to the e to the negative x over 2, which does in fact have a sum of 0. So I did verify that the equation is a solution to the differential equation. Next, it asks me to find the particular solution. So this is a general solution because it contains an unknown constant. And what I need to know is I've been given a sketch, or a partial sketch I should say, of this solution, and it happens to pass through the point 0, 3. So since I have one unknown, this unknown c, I can find that by plugging in that value. So I know that when x is 0, y is 3. So I go ahead and plug that in. Anything to the 0 power is just 1. So I end up getting c to be 3. So the particular solution is y equals 3 e to the negative x over 2. So that's how easy it is to find the particular solution. You have that one unknown constant, and they just have to let you know that an ordered pair or a point that the function passes through to be able to find that unknown constant. So then, besides verifying, perhaps they say to find the general solutions to the differential equation. So if I know something's derivative is equal to x cubed minus 4x, I want to take the antiderivative to get the original equation or the original function. Not all of these will be functions. So y equals, so this would, I go up a power, so 1/4 x to the 4th minus 4 halves x squared, so 2x squared, plus c, because there could have been some constant here that when I took the derivative it went to 0. So this is the general solution to that differential equation. If you're kind of wondering, like, what role does the dy dx play? Well, just go ahead and take a look at this, because maybe it seemed like I skipped a step on the last one. So I want to show how the role of the integral fits in with this. So let's say I keep dy on this side, and I multiply dx to both sides, so then it cancels from this side. And then I have it on, comes over there. So if I want to go ahead and solve this, I can integrate or take the antiderivative of both sides. There's an implied 1 here, so the antiderivative of 1 would just be y. I can put the plus c there. All right, so then this is going to require some type of a u substitution. So I go ahead and I say u is going to be 5 minus x. The derivative of that is negative 1 dx. Well, unfortunately, I still have an x there, so this is one that does require an extra rewrite. I'm going to actually make some space here for that. I can move my y plus c down here just so that I have some space. All right. So what I need to do is I need to figure out a value to put in there for x. So I go ahead and I go ahead and solve this for x equals. So I end up getting x equals 5 minus u. So I have 5 minus u times the square root of u du. And then I would distribute the square root of u to both parts. So 5u to the 1/2 minus u to the 3/2 du. So I go ahead and I do the power rule now at this point. So this goes up a power, so it's going to go up to u to the 3/2. I'm going to have a 2/3 out front, so 2/3 times 5 would be 10/3. Minus, this would go up to u to the 5/2, so 2/5 out front, plus c. And then I need to just switch back to x. And then these constants are not necessarily the same, so they don't cancel out. But what I want to do is just write it as plus c just on the one side. So 10/3 5 minus x to the 3/2 power minus 2/5 times 5 minus x to the 5/2 power plus some constant. From here on out, you don't need to put the plus c on the side with y as long as you've written that there is a constant on one of the two sides. All right, so if you need to graph a representation of what differential equations look like, they're not just the graph of one curved function, since they represent so many different general solutions. So we need to use something called the slope field to graph a differential equation. Well, why would we have something called a slope field? Well, recall a derivative represents the slope of a tangent line, so what this is a sketch of all the possible little tangent lines. So that's kind of why they look like little tangent lines. So this is referred to as a slope field. So you can put a particular solution on a slope field if you know an ordered pair that the equation passes through. So for instance, let's say we knew that we had a particular solution that passed through like 0, 6. So 1, 2, 3, 4, 5, 6. So then how you would sketch in a particular solution is to just follow these as little tangent lines. So roughly that part of the curve is going to go up there, and this part here is going to be going down this way. Or what if it had said that there was a particular solution that went through the point 1, 0. So I go here, and then I just kind of follow these as tangent lines. And something about like that. So you just follow those. It kind of feels like to me like a connect the dots. You're just kind of following those to get a general shape for the particular solution. So eventually you're going to be asked to sketch some slope fields. You would for sure not be asked to sketch anything to this degree, because if you notice that there's hundreds of little dashed lines on there, the most you would do would probably have like 20 dashed lines, but anywhere probably between 9 and 20 is pretty typical for sketching by hand. Usually these are sketched using technology because that just makes the most sense. But a skill that you do need to have is to be able to look at a slope field and identify or match up a differential equation that goes with it. So and remember that this is representing all these different general solutions. The constant value can have different effects on the graph. Oop. So sometimes when you're looking at these, you can tell that the general solutions will just be vertical translations or shifts of each other, but that isn't always the case because we'll be looking at a wide variety of differential equations throughout this year, and you'll find out why that they aren't all just vertical translations soon enough. So what we're going to do is I'm going to give you here 4 slope fields and 4 differential equations to match them to. How we're going to identify what they match to is to actually try to find some slopes of tangent lines and try to see which slope field that seems to match up with the best. So if I have the differential equation dy dx equals 0.5x minus 1, what I want to do is I actually want to plug in some different x's and y's just to kind of see what's going on. So for instance, I like to pick 0, 0 as kind of one to start. So if I plug in 0, 0, I end up getting a slope of -1. If I go ahead and look at these, is there any of these that seem to have a slope of -1 at the origin? And there is one that meets that criteria. It looks like B is the only one that has a slope of -1 at the origin, so this one can be matched with B. All right, so let's look at this one here. So if I have the derivatives equal to 0.5y, so xy dy dx, So if I plug in the origin, so 0, 0, the derivative up, so 0.5 times the y coordinate is 0. Notice x isn't playing a role on this one. So are there ones that have a derivative of 0 at 0? Well, doesn't seem real conclusive, so maybe I should plug in some other points just because I'm not necessarily seeing a horizontal tangent at 0, or there's more than one. So let's plug in another point, like maybe 1, 1. So 0.5 times 1 is 0.5. So let's just maybe plug in a couple other points just to check. So like -1, -1 would be like -0.5. 1, -1 would be still be -0.5. Let's go ahead and take a look. So if we're at 1, 1, see 1, 1, so we have slope of a half, that matches up. If we were to look at 1, 1 here, this has a negative slope, so that's not going to work. If we go up here, 1, 1 has a positive slope, so that's not going to work. So it seems like it's going to match up with C, but let's just double check at the point -1, -1. I'd expect to have a slope of -1/2. Yep, that seems to match up, so I'm going to say that this one does go with C. Okay, so I have dy dx equals -x over y. So again, I just make a table. So if I start with 0, 0, that slope actually, I can't divide by 0, so that actually doesn't have, I can't take the derivative at 0. So if we plug in 1, 1, I'd get a slope of -1. If I plug in -1, -1, a -1 divided by a -1, and the opposite of that would still be -1. If I were to plug in like 1, -1, I would just get a slope of 1. So let's just kind of take a look. So A and D are my options. So if I go up to A, at 0, 0, there is no slope, so I guess it's kind of hard for me to tell what's going on right there. But at 1, 1, the slope is supposed to be -1. So 1, 1, oh, that has a positive slope, so that's probably not, that's not going to work. So let's go ahead and take a look at this one. At 1, 1, this does have a negative slope, so that seems reasonable. At -1, -1, that also has a slope of -1. At 1, -1, that has a slope of +1. So this is following those patterns. Okay, and then so last but not least, then we would say that this would match up then with A if this were a matching problem. Okay, so that would be a way to be able to match up a differential equation with a slope field. And again, later this unit, in the next lesson, we will be talking about how to come up with a sketch of a slope field for a differential equation. All right, so let's just look at one last example here. It says for the differential equation x y prime minus 3y equals 0, verify that cx cubed is a solution and find the particular solution determined by the initial condition y is 2 when x is -3. Okay, so if we need to verify that that's a solution, we need to show that this is true. Looks like I'm going to need a derivative as a part of that. So if I go ahead and take the derivative, I'd get 3cx squared. So x times y prime minus 3 times y. Well, this here would simplify to 3cx cubed minus 3cx cubed, which does equal 0. So we did verify that that is a solution to that differential equation. So this is a general solution because it has a constant. The initial condition that we're given is that this passes through the point -3, 2. So we want to go ahead and plug that into the equation. So where I see a y, I'm going to go ahead and plug in a 2. And then x is -3. So -3 cubed is -27. So then c would have to be -2/27. So the particular solution then would be y equals -2/27 x cubed. All right, so in this lesson we reviewed what a differential equation is, that it represents the derivative of a function. The solution to a differential equation is working backwards, taking the antiderivative, finding the original function or family of functions that that meet the criteria of the differential equation. A general solution has an unknown constant in it, and a particular solution represents a unique equation or a unique function. And then slope fields are the graphical representation for how the different types of equations that are solutions to that differential equation.